All right, welcome back. Here we have the final section of the Unit 2 review for the exam. And in section 2.7, we're looking at molecular geometry. Molecular geometry essentially is just looking at the shape of the molecules. Two things to remember here: that the molecular geometry is dependent on a couple of items. It's going to be dependent on VSEPR, and so theory. And so remember here that the VSEPR theory is going to be the valence shell electron pair repulsion, and it's this R value here that's very important because this is essentially repulsion. We're looking at repulsion occurring largely because of the lone pairs that exist. Now, I'm not going to go through all of the different molecular geometries in detail, but you should be familiar with a couple of items here. Whenever there's repulsion, particularly coming from lone pairs, otherwise known as the unpaired electrons, remember that these lone pairs are going to have a larger electron cloud. And that's what's going to be driving a lot of the shape of a molecule, largely because of the repulsion that these lone pairs are going to exert. And so you got to keep that in mind. And it's typically the repulsion occurring, especially if these lone pairs occur at the center atom. So a couple of the structures that we'll look at here are going to be the following. So let's say, the dominant structures that you should know about are the ones that are going to be in linear form. So that's when you have two atoms or when you have three atoms. And I'll draw the center atom as that. But notice here in either of these cases, you can have lone pairs on either end of a two-atom molecule. That isn't going to affect the geometry at all because essentially that's the maximum distance that you can have. And so in this particular case here, the maximum distance that we're referring to is the distance from one atom over to the other. That's going to be 180 degrees. Okay. In the example of the three bonded structure, you can have lone pairs over here at the end, lone pairs at the end. That's okay. But if you don't have any lone pairs in the center, that's also going to be okay if there aren't any, because that's what you prefer. That means that the overall angle here between these two atoms from one side all the way to the other, that's also going to be 180 degrees. And that's actually the preferred. Now, the second you start adding electrons to the center atom, and I'll just draw this three bonded atom here or molecule just to show you. If we were to add a lone pair here, remember that lone pair is going to have a electron cloud here. And it's pretty large. And so when you consider the cloud that's already associated with each of the other atoms, and let me draw that here, you can see that cloud is actually going to cause a little bit of a repulsion. So that's going to push down on these two bonds. And so ultimately what you're going to wind up getting here is you're going to wind up getting a structure where you've got that center atom here with the two atoms bonded downwards at an angle. And so that's the structure there. Now you could also have a second pair of lone pairs at the center atom, and so you can have that structure there, or you can have the structure here. Let's just draw this a copy here. You can have another one here, a little bit more, in which case that's going to change the angle a little bit for both of these. And so let me just show this one here. You're going to wind up getting two electrons here. And so what that will happen here, if I draw in the angles appropriately here, what will happen is that angle will actually get a little bit smaller overall. You're going to wind up seeing this angle kind of get a little bit smaller over here. Overall, the distance here between these here, this angle here with a one lone pair is approximately 120 degrees, but if you have two lone pairs, the angle here is closer to about 109-ish is what you'll see in terms of an angle. Now the names of this. Now this particular one that I just drew, these two here are called bent structures. The angles are important, so just keep that in mind. The ones that I drew up at the top, these were both linear examples. And the only difference between these two, obviously, is the lone pairs at the center. So whenever you include the lone pairs at the center, you're going to get a bending of the overall angle of those bonds. So let's go to make a little bit more room here and kind of continue our discussion. And so what kind of other structures do we have? And so a couple of those structures include, what if I have a center atom that is bonded to, say, not just one, not just two, but instead of a lone pair to the top, if we have one single bonded atom to the top here. The angles associated with these here, this is going to be 120 degrees in each of these. All of these are congruent here. And the idea is that at each of these here, this bond here on all three positions, all of these are considered electron groups. And so the electron groups is essentially going to be that entity that is going to be affected by the repulsion. And so in here, what you can do is you can use the equation here, the electron group number, and you can use that as a denominator or a divider over the total angles of 360. So in this particular case, I had 360 degrees, I have 3 electron groups, and so that's what's going to lead here to the angle of 120 degrees overall that we observe right there. Okay. This particular structure here has a name to it. This is, notice here, if I can go in here and draw the connection of these dots here, if I were to draw a connection here, here, and here, notice the shape is a triangle shape. And so we would call this particular structure a trigonal pyramidal. And the unique thing about this particular shape here is that this is going to be flat. It's a flat shape. So if I look at it from the side, you're going to see at the center atom, it'll resemble the 3 atoms from the side. But if we actually tilt it a little bit, you can see that the other one is back here, there. And so we'll draw this one here kind of like a wedge coming at you. So that's kind of what that looks like there. Okay, so that's the trigonal pyramidal. If I take here on the flat side of things, and let me just kind of erase this a little bit to kind of make things, since I know that there is a atom in the back, and so let me just draw it like this way. If I come in here then and then apply to the center atom here, if I apply a lone pair, so if I add a lone pair like that, that lone pair essentially is going to cause this particular structure to actually take on the additional structure here. We'll have here the center atom, the side atom, and then we'll draw that one there. Put the lone pairs up top. Remember, it does have an electron cloud that is actually pretty noticeable, pretty dramatic. You'll see that there. And you can already see if I draw little yellow clouds around this one, you can see that there's not enough space for them. So what's going to wind up happening here is that this electron is going to push things down for all of these angles, which essentially is going to give you the structure where you're going to have a bent scenario, but among all of the bonds in place. So you'll have one of the center atoms here. Now you start to see the bending here. This one comes out towards you, and then the other one comes backwards. And that lone pair is at the center atom. This particular structure here is also a trigonal shape, but because of the bending, it actually now takes on a pyramid, like a 3-sided pyramid. So this one here would be trigonal pyramidal. And so what I need to do here, I need to go back because I had actually called the other one trigonal pyramidal, but actually that's actually incorrect. This is actually the trigonal planar. I'll just identify that here. So, planar for that one there. So let's just write it one more time nice and clearly here. Trigonal planar. Sorry about that. I just realized that when I was writing it down. I had indicated that it was flat, but I wrote down pyramidal. I should have written down planar. Okay. And so that would be the fourth structure here, the trigonal pyramidal. Now, if we take this lone pair here and replace it with a atom instead, you'll see that that particular structure resembles this structure here. You've got one going backwards, and so this particular structure here is called the tetrahedral. Okay. Now, there are a couple of others. You should pay attention to those. Go on to fet.colorado.edu. Take a look at the seesaw geometry. Take a look at the octahedral. Take a look at the bipyramidal shapes as well that exist there. Also the T-shape, to be familiar with those. But essentially, when you look at these and you're looking at that, the main thing you got to remember is how is this kind of important to us? Well, this is going to inform the discussion around the shape, also in line with hybridization. So let's kind of take a look at that discussion here and kind of bring this review to a close. And so let me move some of these items out of the way, move them this way. And so the last section here that we'll deal with is going to be hybridization. And so in the hybridization section, the main thing that we want to know is what kind of shape are we going to have. And this largely is tied to the number of electron groups. Okay. And so the number of electron groups here, which I'll refer to as EG, is going to dictate some of the things that happens. And so the hybridization can be generally derived into a couple of, let's start with a very small one here, and that's going to be SP. Then you've got SP2, SP3. Then the next one here is going to be SP3D, and then you've got SP3D2. So obviously the one over here at the very end, I'm going to underline that in red. That's the biggest. And then the smallest is the one underlined in green. And so what does this really mean overall? What this means in terms of the SP, that means here that we've got an S bonded to a P, or hybridized combined with a P. And then it's just an incremental increase for all the others. So for the SP2 is a suborbital S with 2p suborbitals. And then the SP3 would be 1s combined with 3 p's overall. And then the SP3D is 1s, 3 p's, and then you're also going to have 1d. And then finally the SP3D2 is 1s, 3 p's, and then 2 d's. Now, why is this important? Because if you count the electron groups, we can actually determine what kind of angles they're going to be. So whenever we look at SP, this essentially is going to be the angle here of approximately 180 degrees. SP2 is essentially going to give you a 120 degrees. SP3 is going to give you that angle that's a little bit closer to about a 105, 109. The angles associated with the SP3D, you're going to get 90 degrees of angles here, but you're going to get those at the angles in the center relative to the atoms that are essentially radiating out from the center, but also when you kind of look at the outer atoms on that center plane, the 90 degrees is going to be relative to that. And so essentially, if I can draw that here quickly, here you've got a center atom here, center atom, and then along the plane, you're going to have an atom, and so you have another atom this way, and then you might have a third this way. And so the angle that we're looking at as the angle of interest is going to be the angle right here. Between this one and here, there's the angle right there, 90 degrees. Now these other angles over here, which I'll draw them here, this one here, this is going to be approximately 120 when you look at those there. And that would be typical of the SP3D, because you've got, in this, you're going to have 5 groups of electron groups there at the center. Now the SP3D2, there you'll also see 90 degrees here, but the 90 degrees is more of something that's distributed between not only the ones that are going vertically from the core, but it radiating out as well, because essentially you're going to have, in this particular case, you've got the center, you've got one coming out this way, one coming out this way, one going back, one going back. And so what you wind up having here is you get your 90 degree angle here, and then you also get 90 degree angles right here relative to that. So 90 degree angles all the way around. Okay, I encourage you to take a look at the PhET simulator. That'll have all the information you need. And so that address there is phet.colorado.edu. And what you want to look at there is look at the molecule shapes lesson. And then you can take a look at that and play with all the structures. A lot of the molecules that we had on the problem set are also identified here, so you want to take a look at that as well. All right, that'll conclude the review for this exam that we're having. Remember, the exam is on the 9th and the 10th. That'll be the Tuesday and the Wednesday. And so if you have any questions, come and see me on Monday or during class on Monday. If I see you on Monday, otherwise, try to get me sometime during the day, ask the questions you need to ask, and get those resolved for you before the exam. Other than that, I hope you continue your studies. Make sure you finish reading Chapter 8. That's the applicable chapter for this unit exam, and we will see you on exam day. With that, have a good evening, and we will talk to you soon.